Hello everyone, I welcome you all in my channel Learn Math Easily. Today's in this video, I am going to discuss some of the very important properties of right cosets. These are very important from university as well as if you are preparing for any kind of entrance exams. These properties are of utmost importance. And if you are solving some problems, then these properties are very useful also from application point of view. So let's start with the first property. But before I'll begin, I want to tell you that in order to understand today's video, you need to understand what and all videos I have uploaded on the basis of cosets, because if you will not understand the meaning of concept and the examples based on it, you will not be able to understand its properties. So let's start with the first property. A belongs to HA for all A belongs to G. Whatever element you are getting multiplied with the coset, that particular element will always belong to that coset. That you have to prove. So let's start with the proof. For all A belongs to G, A is equal to EA. Now E belongs to H and A belongs to A. Therefore, A belongs to HA for all A belongs to G. Second property, A belongs to H if and only if HA is equal to H. Suppose A belongs to H. Since this is an if and only if condition, so necessary and sufficient both part we have to do, means given part and the converse part. Suppose A belongs to H. Let X belongs to HA. Therefore, X is equal to sum H and A for sum H belongs to H. Now, H belongs to H, A belongs to H, therefore their multiple belongs to H because of closure property, by closure. Therefore, X HA contained in equal to H, first part. Now conversely, now we will prove H contained in equal to HA. Let X belongs to H. Then we have X is equal to XE. We can write it like XA inverse A. Sorry, I forgot one step. You can write this as A inverse A. So this will be XA inverse A. Now XA inverse belongs to H. This belongs to A because A belongs to H, implies A inverse belongs to H. Also X was the element of H, therefore XA inverse belongs to H. Therefore this belongs to HA, therefore H contained in equal to HA. From 1 and 2 we got H is equal to HA. Now we have to do the converse part. Conversely, let HA is equal to H. Since from first property we know A belongs to HA, which is equal to H, therefore A belongs to H. So this proves the second part. Now second part is very important among all the properties. Second is the most widely used property from application point of view, I am telling. Third property, if G is a finite group, then order of HA is equal to order of H. Let's start with the proof. Let order of H is equal to K. Since G is a finite group, so H being a subgroup of G will also be finite. Let order of H is equal to K means H will consist of K number of elements, H1, H2 and so on HK, where H1 H2 and so on, Hk are all distinct. Now take coset HA, means every element of H is getting multiplied with A. So H1A, H2A and so on HKA. Now all these elements are different from each other. Suppose if possible HIA is equal to HJA for some I not equal to J. HIA, here A is there. Now by cancellation property we have HI is equal to HJ for I not equal to J, a contradiction. Because all the elements of H are distinct. Because all the elements of H are distinct. Therefore, H1A, H2A, H3A, there are no commas here, H4A and so on, HKA are all distinct. Therefore, order of HA is equal to order of H, which is equal to K. Now, fourth property, which some authors used as a theorem also, but the book which I consider, there I got this as a property only, not as a theorem. HA is equal to HB if and only if AB inverse belongs to H. So this is also an if and only if condition. So we have to take into considerations both the given part as well as the converse part. Suppose HA is equal to HB. Let A belongs to HA. Obviously A will be element of HA. Cancel this A. A belongs to HA. Write since here. Since A belongs to HA, which is equal to HB. So A belongs to HB. So A is equal to HB for some H belongs to H. So AB inverse is equal to H belongs to H. Therefore AB inverse belongs to H. Conversely, suppose AB inverse belongs to H. Then AB inverse is equal to H for some H belongs to H. So A is equal to HB. This is your equation number 1. Let X belongs to HA. Then X is equal to H dash A for some H dash belongs to H. So X is equal to H dash HB from equation 1. By associativity, we can write it like this. This belongs to H, H dash H, and B belongs to B. Therefore, X belongs to HB. Therefore, HA contained in equal to HB. This is your equation number 2. Also, AB inverse belongs to H. You forget this part and notations whatever I have used till here. Let AB inverse belongs to H implies AB inverse whole inverse belongs to H implies BA inverse belongs to H implies BA inverse is equal to H for some H belongs to H. So B is equal to HA. Let X belongs to HB. So X is equal to H dash B implies for some H dash belongs to H. Now X is equal to H dash HA, which is equal to H dash HA belongs to HA. Therefore, HB contained in equal to HA. This is our equation number 3. From 2 and 3, we get HA is equal to HB. Therefore, HA is equal to HB if and only if AB inverse belongs to H. Now that was the end of last property. Now in next class we will going to prove the theorems which are based on the topic of cosets. And after that we will start with the new topic of group theory, that is equivalence relation. That was next video will be the end of in upcoming 2 videos I will complete the topic of cosets. The same video is available in Hindi language also. If you like the video, then don't forget to hit the like button. And in future, if you want to see such kind of videos for higher mathematics, then don't forget to subscribe for my channel. Thank you so much for watching this.